Welcome back to our Topic 3 on Power series in AP Calculus BC. At this point, we've really learned our four major Maclaurin or Taylor series that we need to have memorized. And remember, when we say Taylor series, we really mean a Taylor series centered at x equals 0, so a Maclaurin series. So there are, I guess, 5 equations you need to have memorized so far. The first are the 4 Taylor series, and you should know what they are, and you'll practice writing them out in just a bit. So you have e to the x, and then I'll do 1 over 1 minus x next to it, and then maybe splitting this guy in half, give or take. Over here, we're also going to have cosine of x and sine of x. I mentioned 5 equations, though, because, of course, the 5th equation you should have memorized is the general form of any Taylor series, which is, of course, you're like f of a over 0 factorial times x minus the center to, and so on and so forth to the 0th plus blah, 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 blah. And you can always go back to that to derive these 4, but I think you'll find your life becomes much easier if you can keep these 4 memorized. So why don't you take a quick second to write these out, maybe go out a couple terms, and then don't forget to include your summation at the end. Good luck. Okay, running through these ones quickly. Our e to the x is, I think, very, very similar to 1 over 1 minus x, which I think is kind of interesting, right? Something like this. And then we're going to sum up from 0 to infinity of just x to the n over n factorial. 1 over 1 minus x, even a little bit easier, just plus x, x squared, x cubed. That's our geometric Taylor series because you multiply by x every time starting at 1. And we sum up from 0 to infinity. Well, what is the sum? I think this is just going to be x to the n. And don't forget that this is the actual sum of a geometric series. Moving on, cosine. This is an even function, even exponents. So it may help you to start with this, and then we always alternate in sign. And 4 factorial minus x to the 6th over 6 factorial. And we should probably go through and do our summation here. Need a little bit more room, but it shouldn't be too terrible. 0 to infinity. Don't forget that alternating in sign. And then we have our fraction. Looks like x to the 2n over 2n factorial. It looks pretty good. And then sine is our odd function. So same idea, but making sure that we start at odd exponents. There we go. And, ooh, that was an interesting sigma there, Mr. Grant. Good. From 0 to infinity, negative 1 to the n again. But this one, I think we need to change our exponent slightly. It needs to be 2n plus 1 over 2n plus 1 factorial. Nice. Now, something interesting happens when we start to compare the graphs of these functions. For example, if you were to compare the graph of sine of x to the graph of its Maclaurin series, you would find that the more terms you give sine of x, the more accurate the Maclaurin series becomes. And if you were able to write an infinite number of terms, all of the terms, if you will, for the Maclaurin series for sine, you would find that it is exactly the same as the entire graph of sine of x. And that is also true for cosine, and also true for e to the x. However, that's not true for the geometric Taylor series. No matter how many terms you write over here, it will only be accurate for the 1 divided by 1 minus x for a small interval. And so what we're going to try to determine today, and this is what our point is saying down below, is why infinite series only match up to a small piece of some functions, like our geometric Taylor series, excuse me, but for others, exactly match the function. So what I have prepared for you is a nice DESMOS activity that I built, and it's nothing amazing, but I think it will do a nice job of showing you why some functions match and others don't. So the link is up here. If you're working on a PDF, you can just control click if you're on a computer, regular click if you're on a mobile device, or if you wanted to type it all out, this is LGL PB as in peanut butter 77D1K. So it should take you to a DESMOS activity where on DESMOS, I wrote out all the instructions, but because you guys won't be able to edit it, I rewrote all the instructions here so that you can actually fill in the blanks. I would like you to try it on your own, and then if you get stuck, or if you need to, of course, fill in a blank or something, you can come back to this. I am going to walk through the entire thing, but I think you will probably move much faster than I. So go to it. As you need various answers, such as number 4 down here, you can come back to my video. You might be able to get it on DESMOS. I'm excited to watch your success. You are done once you get all the way through 12 here. And then through 12, we're going to go back and discuss all of these answers, try 3 examples, and we're done. There are some practice problems at the end. So this one seems a little bit longer, but I think you'll find the DESMOS activity goes pretty quickly, and that takes up the majority of the pages. So ready, set, go. All right, and I'm going to go ahead and work through these as well. So let's see what we can do here. Set I equals 0 and A equals 0. I did that. Then click on the open circle next to item 4. So 1, 2, 3, 4. Here's item 4. Click on the open circle. And the power series of 1 divided by 1 minus x should appear. I'm going to turn on projector mode so it's a little bit more bolded and visual for you here. The graph in blue is the power series of 1 divided by 1 minus x. So they're saying this is the, it looks like it's centered at 0. So this is the Maclaurin series for 1 divided by 1 minus x. Okay, and it looks like so far the Maclaurin series does not match 1 over 1 minus x at all, does it? Notice the 2 parts over here, besides sharing this one single point. Okay. They, of course, have identical y values at x equals 0 and I equals 0. Not a surprise there. Adjust the upper limit of summation. Well, the upper limit of summation is, I think, going to be this I right here. Upper limit of summation, I to give more terms of the Taylor series. So currently we're at a 0th degree polynomial, which is always a horizontal line. If I give it 1 degree, we get a tangent line, because now we added on plus x to the first. And now, at least at this point, 1 over 1 minus x and the tangent line share both the value of y and the value of y prime. They share the same slope. Okay, now what are we doing? As we increase I, the blue graph starts to better approximate this. No matter how high you increase the degree, though, the blue graph never follows the original graph outside of what interval? Oh, battery level's critical. Well, hopefully it'll survive. If not, I will be okay. So I'm going to go ahead and start to increase this, and notice we see the blue graph is getting closer and closer to our 1 over 1 minus x, but it looks like it's hit a wall, and it's actually hit 2 walls. It looks like it never is going past, what is this, about an x value of -1, and it also is never jumping over to +1. It looks like it's constrained between -1 and +1. And you can give way more terms than I only have 33. And it always takes DESMOS a little while to catch up because it's doing really big calculations every time you put in all of these. So it may actually freeze your computer or your phone if you go too far. But yeah, I think no matter how far you want to go, you're really stuck. So it looks like it does a really nice job of determining values between -1 and maybe +1, but nothing better than that. So where are we so far? Let's see, we did that already. We did that already. Okay, so scooting on down. How far away is the end of the interval? And actually, I should add a few more terms over here. There we go. Is the end of the interval from the center of your graph. Okay. Now, well, my graph is centered at an x value of 0. I think the total distance where it looks like my blue graph, and I think we have a fancy word here, converges. My blue graph converges to the red graph is a distance of 1 in this direction and 1 in the other direction. You could argue maybe just less than 1, right? Because it's not actually reaching here because there's an asymptote there. But yeah, it looks like my Taylor series only converges to my original function in a distance of 1 in each direction. That distance to which the function converges is known, and here's our new buzzword, as the radius of convergence. So that's right here. So the radius of convergence for my Taylor series, because I can only go a total of 1 in each direction, is r equals 1. It turns out that this radius is always symmetric. So from here, it's always going to be the same amount in each direction. So if it's 1 this way, it's going to be 1 that way. All right, so now we're going to move I back to 0 again. Oops, don't think I needed to do that. We're going to move I back to 0. That looks pretty good. Cool. And then what? Now adjust A, which is where the Taylor series is centered. And for each value of A, experiment with slider I. What's the radius of convergence for each value of A? And it should be different each time. So I think that's on our next page. And look, they give you a whole bunch of values of A here. -4 down to -1, not 0, because we just did 0, and then 1 to 4. So we'll try to work through all these. Let's start with, I don't know, -1 is pretty close. So let's move A to -1 and watch my center change. There we go. Now I'm centered at the point -1 comma whatever that is. And now we're going to use I again. And let's see how far this radius of convergence is. I think we can already see where we're converging. It looks like it's a distance of 2 to the left and also 1, 2 to the right. So this one converges a distance of 2. And I imagine you guys are going to figure out the pattern pretty darn quickly because that's not a crazy one. But let's try maybe one more -1. So resetting to 0. Let's try centered at -2. Add a few terms on here. Oh, and look at that. From -2 to -5. Now it's a distance of 3 in each direction. Right? And you might even be thinking, well, if you wanted to get really nice, if you wanted to be able to use your Maclaurin series here, it might make sense to center this really far left, because then you're going to get a really big radius, and you'll be able to use your actual Taylor series to calculate more values. All right, so we took care of those. I think you can see your pattern, right? This next one's going to be 4. Last one's going to be 5. What about positive values? Let's start at 4 maybe. So here's this. They asked us to go to 4. That's the far end. Centered at 4 over here. Cool. Let's add some terms. I think we can see it already. Yeah, it's going distance of 1, 2, 3 in that direction. 1, 2, 3 in that direction. Yeah, radius of 3 when this is 4. And then let's drop it down, right? We can, I think, probably just change the value of A here. Let's go to 3. There we go. And it looks like I have a radius of 2. At 2, I have a radius of just 1 in each direction. So 3, 2, 1. What about at A equals 1? A equals 1. Oh, it's disappeared. Why did it disappear? Oh, because aren't we centering it at A equals 1? And where is 1 on the graph of 1 over 1 minus x? Well, if you substitute in 1, you get a discontinuity. It does not exist. It's an infinite discontinuity. There is no point. And if you try to create a tangent function, a Taylor series at not a point, there is going to be no tangent function, no Taylor series. So in this case, I would say that there is no radius of convergence, right? You could just say like the empty set, nothing there. Cool. All right. What seems to dictate the length of the radius of convergence? Well, that is an interesting question, right? If we look back here, and maybe we'll jump back to our original one, which is centered at 0, why is my function stopping? Well, to the left, it doesn't look like there's any reason it should stop, but to the right, it seems to be hitting an invisible wall every time. And doesn't it look like it's hitting the asymptote? So I think, and jumping back over here, what seems to dictate the length of the interval? Well, I think the asymptote that's in the original function is dictating the length of the interval. So if you take the distance from wherever you center it to the asymptote, won't we know our radius of convergence? Yeah? So for example, if I wanted to center this at -4 over here, the distance from -4 to my asymptote, +1, is 5 units. 1, 2, 3, 4, 5. And so it looks like I stop at the asymptote, and so my radius will be 5. So why can our Taylor series, which is a polynomial, not perfectly approximate the entire graph of 1 divided by 1 minus x? Well, think about characteristics of a polynomial. A polynomial is that function ax to the n plus bx to the n minus 1, so on and so forth. But in particular, our polynomial is continuous everywhere. Right? It has to be continuous. And so how is a polynomial going to take into account an asymptote? Well, there are no asymptotes in polynomials, so it just won't. Essentially, our polynomial cannot approximate this graph because it doesn't know how to deal with asymptotes. So it basically says, okay, asymptote, I give up. That's as far as I can go. The other question about that radius of convergence is, how does symmetry play a role? And again, this goes down to polynomials, because all polynomials have some sort of symmetry. You might have to play around with it a bit, but it does have some sort of symmetry here. And in terms of symmetry, wherever you center it, however far you go to the right is the same distance you go to the left. So if there's something limiting the distance of the polynomial on one side or the other, it will automatically be limited on the other side. So since there's an asymptote 5 units to the right, the function will also stop 5 units to the left. All right, what's next? At this point, go back up to item 4, click the filled in. We're going to turn off 4, A, I, 0, and go to 16. Okay. A and I need to be back down to 0. And we're going to go to item 16. That's quite a ways down here. 9, 10, 11, 12, 13, 14. It says 16, but I think it actually means 14 here. So we're going to have to change that a little bit. Hopefully I'll have it updated on your papers. So turn to item 16. We're going to turn it on, and we're going to see the e to the x and its Taylor series in green. So turned on. There we go. Everything else is there. Nice holiday colors. Very exciting. Okay, before you alter your center and your number of terms, what do you expect the radius of convergence to be for this Taylor series? Basically, where will this green function stop approximating e to the x? Well, we should start to think, are there any limiters on this? Does e to the x have any vertical asymptotes or any discontinuities? And I can't think of any. I think e to the x goes diagonally up, even though it looks like straight up. It goes up to infinity to the left, and to the right rather, and to the left. It goes forever, just kind of sitting right above 0. I think there are no limitations here. So let's see what happens, and maybe I'll show a little bit more of the graph. Let's give a few more terms here. Okay, I'm only at 3 terms, and we're doing pretty well. Look at that. To the right, you already can't tell the difference, and to the left, as you give more and more terms, look at that green function just kind of wrap around. I always think of it as like curling around the function, and it's like a vine growing on it. But yeah, I think it's going to go forever. We can see that pattern. So I think this is one of those functions then that in terms of a radius of convergence, there are no limitations. So my radius here is infinite. There's an infinite radius of convergence. It goes forever, because the Maclaurin series for e to the x will exactly evaluate e to the x. It will exactly match it. Now, what happens if we use different centers? Well, I don't think anything's going to change, because no matter where it's centered, there's no limitation left or right. But let's make sure I'm not lying to you, so maybe let's center it, I don't know, at -2. That's a pretty nice center down here. Let's give more terms. Okay, and there we go again. So the nice part about functions like this, like e to the x, is if you know that the radius is infinite for any center, then you should really go through and pick the center that makes the most sense for mathematical operations. And because we've seen e to the 0th, and in fact every derivative of e to the x is e to the x, so e to the 0 for every derivative all the way down, e to the 0th is 1, then I would argue that if you ever wanted to use a Taylor series for e to the x to approximate a value of e to the x, we should probably always center e to the x at 0. There's no reason to center it anywhere else, because any other center is going to have the terms of your polynomial be e squared, e something, and so you have to do calculations with e, which kind of defeats the point. But centering e at 0 is really, really nice, because then you can perform calculations of e to the x without actually using e, which is super powerful. All right, we did that. What causes the Taylor series to not converge? We already discussed that. Discontinuities. So we're going to go through and quickly discuss what we've learned so far and try to summarize it and then get to the end of class. The radius of convergence is vital in order to use a Taylor series, because we are not allowed to use a Taylor series to approximate a function if we are outside the useful radius of convergence. For example, if we had the Maclaurin series for 1 over 1 minus x, and as a reminder, that is going to be centered at x equals 0, right? And we also need to remember that there's an asymptote at x equals 1. Well, if we have the center and we know there's an asymptote at 1, then I think that means at most we can just go 1 to the right, and we can also go 1 to the left of 0. Well, let's see. Which of the following x's can you use the Maclaurin series to approximate this guy? Well, 0 is totally fine. In fact, since this is centered at 0, they are defined to have the exact same value here, so sure. 0.5, yeah, 0.5 is between 0 and the asymptote of 1, so there's nothing wrong with that. Negative 0.5, sure, we'll be okay there as well. At 1, ooh, that's tricky. I'm not sure here, but I'm thinking no, because at 1, isn't there an asymptote? And our polynomial can't have an asymptote, so I think at 1, this is going to be does not exist, and our polynomial is going to give us a nonsense answer. It's not going to give us does not exist, so that one's out. Negative 2? Well, no. Our Maclaurin series is going to stop matching my function 1 over 1 minus x right at negative 1, so that's out as well. And positive 2, definitely out. That skips over the asymptote. That's on the other side, so we're no good. Well, what if we use the Taylor series centered at negative 2? Well, then we have a center at negative 2, and we have the asymptote at positive 1. What's the distance between? The distance is 3. So that means I can use any value of x that's smaller still than 1, of course, right? And then what's 3 to the other way? I think it's negative 5, right? Now I'm allowed to use any x value between negative 5 and positive 1. And so I think that negative 2 will work here. Right, so picking that center for your Taylor series is really, really important. And the further you center your Taylor series away from an asymptote, the more values you'll be able to plug in and get sensical answers for. And I'm saying sensical here because your Taylor series, you can plug any number in there that you want. There's nothing wrong with it. It's a polynomial. It will always give you an answer. The issue, though, is that the answer you get will be nowhere near relevant to this guy. Right? Okay, same question, but now use any Taylor series for e to the x. So center it anywhere that you want. Which of the 6 values could you calculate? And of course, all of them, because e to the x is continuous everywhere, no discontinuities. Okay, so there is actually a theorem, and you don't need to memorize this, that says the radius of convergence of a power series centered at A is equal to the distance from A to the nearest point where f cannot be defined in a way that makes it holomorphic. And holomorphic is essentially differentiable in the complex plane. So meaning there are slopes even using imaginary numbers. And this is well past the scope of the course. But you can go down the rabbit hole and talk about holomorphic, talk about what it means to be differentiable in the complex plane, and then come back and teach me if you'd like. But ultimately, all the theorem is saying is that if you have, and we're really just going to focus on the real numbers for today, if you have a discontinuity on your graph, then that is going to be the bounding factor for our Taylor series. Now, if you have a graph of a function, determining the radius is really not that hard, right? You just count. You're like, here's the center, here's the discontinuity, that's my radius, I'm a winner. But it gets much harder if you're given a power series and you don't know what the graph or what the original function is. And in this case, we're going to need a test to determine our radius of convergence. However, the words radius and convergence should be ringing some bells. We are going to use the ratio test to find the radius of convergence, because remember that this shows convergence for a geometric ratio, and we know that our answer for our geometric ratio in the ratio test has to be between 0 and 1. So what we did in the past is we found a radius by examining the ratio of two infinitely large terms, and really they should be the absolute value of these. Okay, and when we originally did this in topic 2 with our infinite series, we left off the absolute value because we were quickly able to look at it and say, oh, it doesn't matter. All of our terms are going to be positive because n is always positive, so nothing too bad here. What's going to end up happening, though, is because x can be negative values, we are going to want to throw in those absolute value every single time, and we do need to keep it all the way through. Okay, so ultimately what we're doing is we're testing for absolute, remember these, absolute convergence instead of conditional convergence. So we state our ratio test like so. A power series in this format, like all Taylor series, Maclaurin series, converges if the ratio of those two consecutive terms at infinity is less than 1. And in fact, we're going to go even a little bit further here. The way that we conclude the ratio test with a power series is we need to simplify down this test so that our final answer in here is just the center of the series. If there are any other numbers attached to this, we're going to have to move them to the other side, and we're going to talk about that math in just a second. If, when you finished isolating this part that shows the center of your series, then whatever your value of r is on the other side, currently it's 1, but it may change, is going to be the radius of convergence, right? So what that tells you then is that if this is less than r, then your power series will converge. And of course, the opposite is true too, and it's easier to see with numbers. If, however, you get an answer of infinity, then it means our radius is infinitely large, and so our power series converges for all values. And that should make sense, right? If we have a center right here, and they say, oh, hey, your radius is infinitely far, then that means you can go infinitely far this way and infinitely far this way, and so we'll converge everywhere. However, if we get an r value of exactly 0, then our power series is only going to converge at the center. And we'll see some examples of that in just a second. Because don't forget, when you create a power series, right, if we have some sort of function over here, and then we have our power function coming out here, and I only have two terms there, they have to share that center point. So if you have a radius of 0, it means for some reason you can't use your power series in either direction, but of course it will still work at the center. Let's rock and roll. Find the radius of convergence for each of the power series below. All right, write small, be ready. Limit as n approaches infinity of, well, -1 to the n plus 1 over 4 to the n plus 1 times x plus 3 to the n plus 1, all divided by -1 to the n over 4 to the n times x plus 3 to the n. Things to note, absolute value, we don't care about the negatives, they won't affect anything at all. We are going to have to multiply by the reciprocal of this other guy. We'll do a little cleanup as well, and since you guys have already done this before, I can move a little bit quicker. X plus 3 to the n plus 1, split into 2 pieces. Same base. Split the 4 to the n plus 1 into 2 pieces. Times the reciprocal, 4 to the n over x plus 3 to the n. Looking pretty good. What can we cancel? A lot. And then from here, I think there are no more n values, so we can actually drop the limit. Doesn't matter anymore, right? And so we end up with 1/4. I always like to write this out in front of x plus 1. Okay, and what do we know about the ratio test that has to happen for our series to converge? Well, the answer to the ratio test has to be less than 1. And so as long as this inequality holds true, our series will converge. Notice that x plus 1 isn't isolated though, and this is 1/4. Now it turns out, and absolute value is kind of weird this way, if you're multiplying or dividing by a value on this left side, you can multiply both sides by that value, right? You can kind of think of it as distributing absolute value here. The absolute value of 1/4 is 1/4. So I'm going to get rid of that 1/4 by multiplying both sides by 4. And that's going to give us the absolute value of x plus 1 has to be less than 4. What is this telling us? Well, what this is saying is we have a series, so whatever Taylor series this is centered at x equals, be careful here, -1. Okay, so we're centered at -1, and the radius of convergence is 4, which means we are allowed to evaluate this summation for any x value, right? Because remember, these are considered polynomial approximations. If we wanted to find e to the third, we'd plug in 3 here, though this is not for e to the third. We're allowed to use any x value we want, definitely including -1, because it's centered at -1, right? Well, that's awkward. It says x plus 3, doesn't it? I was like, this is not matching up at all. Good job, Mr. Grant. Okay, we should probably fix those 3's here. Doesn't change too much, though, does it? There we go. Centered at -3, and we're allowed to use any x value from -3 up to 4 to the right. Yeah, 4 to the right. Let's see, -3 plus 4 is 1. And 4 to the left. -3 minus 4 is going to be -7. So we can use any x value from -7 to 1 in this function, and it will give us the same value as whatever the original function is. Now, I don't know the original function. You could graph this and try to guess what the original function is, but that's all we're doing, right? There's our radius of convergence. All right, let's try a second example here. On our second example, I'm already suspicious looking at this. This is a power series that doesn't have a denominator. And to me, I'm thinking that remembering back to our convergence tests, right? If we do that nth term test, right, as n goes to infinity of just the individual sequence in here, I can definitely see that that's going to be infinitely large. I'm pretty sure that this doesn't converge ever, right? This is going to be a divergent series. It will never add up to a specific number. But to double check it and just to see what the ratio test is going to give us, because it's kind of counterintuitive here. If we go through, we find the limit as n approaches infinity of n plus 1 factorial times x minus 1 to the n plus 1 divided by n factorial times x minus 1 to the nth. A little bit on simplifying, so it's nice that we're doing this one. N plus 1 factorial, and I would say maybe hold off on writing because I'm going to erase, is n plus 1 times 1 smaller, that's n, 1 smaller than that, 1 smaller, and of course we go until we get to that 3 times 2 times 1. But what do you notice about this piece right here? Isn't that just n factorial? Cool, if that's just n factorial, then why don't we just write n plus 1 factorial as n plus 1 times n factorial? Why am I doing that? Well, on the bottom, we already have n factorial. And so I think we have some nice cancellations going on here. Okay, so I guess I should finish up the top section. X minus 1 to the n times x minus 1 to the first. Canceling. Gone, gone. Cool. Looking at this one more time, we get n plus 1, which is multiplying times x minus 1. Now, we're just taking n to infinity, and we're saying x is a specific number. So if n is infinitely large, and you're multiplying it by a specific number, infinity times a number is either going to be positive infinity or negative infinity, isn't it? So I would say that this limit does not exist here, but it's definitely going to be infinity or negative infinity. So if we're trying to figure out where this is less than 1, and this is does not exist, then I think that we're seeing that this will never be less than 1. And so as our limit can never be less than 1, so as the ratio test never gives a result less than 1, there is no radius of convergence. You could also argue, of course, that you get a radius of convergence of 0, because we are centered at x equals positive 1. And so if you're centered at 1, then you're going to have the same result at 1. But that's really it. All right, last one. Okay, x to the n over n factorial. Don't I recognize that? That looks like a really familiar power series. Isn't that actually e to the x? Right? And I put approximately, but it should be exactly equal to e to the x. And we already talked earlier, e to the x does not have any asymptotes. So I would expect this power series to match e to the x everywhere. So what does this look like? Well, we're going to take the limit, of course, as n approaches infinity. X to the n plus 1 divided by n plus 1 factorial over x to the n divided by n factorial. Clean this guy up a little bit. Oof, that was not pretty. Better. X to the n times x to the first, and then this guy is going to come join him at the top, so times n factorial, and the denominator, n plus 1 times n factorial, right? Splitting this one up. Go away. Times x to the n. Lovely. Simplifying. Nice. And sound effects are non-optional. The limit as n approaches infinity. We have 1 over n plus 1 times, and this is x to the first. I actually like to rewrite that as x minus 0 to the first, because it really, if you get in the habit of always writing this piece at the end, it really helps you see what the center of your series is. This is centered at 0. All right, n is going to be infinitely large, but 1 over something infinitely large is just 0. And since x has to be a specific value, 0 times a specific value is 0. So for any x value, this becomes 0. And isn't 0 always less than 1? Always less than 1. And that's very different to what we got over here, right? This said x has to be specific values to make it less than 4. But here, all the x's canceled, and we got an answer that is always true. So you can think of this as infinitely many solutions, but what really is happening here is that our radius is infinitely large. Okay, so as the ratio test returns a result of 0, which is always less than 1, then the radius of convergence is infinite. Now, this is kind of counterintuitive to what we saw up above because you're getting 0 here. So you might be tempted to think, well, wait, if I'm getting 0 here, shouldn't that mean then that I got a radius of 0? And same thing over here. You're getting essentially infinity. Let's call this infinity for now, right? You're getting infinity. Doesn't that mean the radius is infinite? And it's not. And I can show you right now really quickly why it's not. This doesn't come up too often, but it's nothing too terrible. So let's take this limit one more time. The limit, well, actually, no, let's figure out the answer. So I'm going to go ahead and move x minus 0 to the top of this. So x minus 0. And then we said that this whole thing becomes 0, right? Or rather, let's do x minus 0 and substitute infinity in the denominator. So infinity plus 1 is infinity. Yes? And we know that this has to be less than 1. This is the end of the ratio test here. Well, if you wanted to isolate x minus 0, you'd of course multiply both sides by infinity. And we get x minus 0 is less than infinity. Well, x minus 0 is always less than infinity, right? It might be infinity if you use infinity, but since x has to be a number, you can't use infinity. So you can see then that this is going to be centered at x equals 0 with a radius that's infinitely large. And you can do the same thing over here. And again, this is a bit of an abuse of the notation, but that's okay. If you substitute in infinity, you're going to get infinity times x minus 1 is less than 1. And if you divide both sides by infinity to isolate the center, we get 1 over infinity. And of course, 1 over infinity is 0. So what's happening here is we get x minus 1 has to be less than 0, but you can only be less than 0. Actually, you can never be less than 0. So I think that's just not going to work at all. And so we see that there is a radius of 0. All right, your last problems are just some practice problems, a bunch of ratio tests, nothing too terrible, a couple connection problems, and I think that should be it for today. So thank you for tuning in to our Radius of Convergence. Hopefully you learned a lot and saw that we're really bringing everything together that we've done these last 2 units, which is super exciting. Tune back in tomorrow for the interval of convergence.